another video presentation from Electronics Engineering Graduating Batch of 2016. I'm Engineer Tolentino, and I hope you enjoy watching this video.
Hi, I'm Jemima Lois M.
I'm Ortizano.
I'm Maricris Olayvar.
I'm Dueñas.
And I'm Emerlyn D.
We are the representative of Polytechnic University of the Philippines, Sta.Rosa campus.
We are to present our thesis study under the supervision of Engineer Tolentino.
Our study is entitled
Design and Implementation of Mimicking Robotic Neck, Improving Hyper-Flexion Extension Movement, and Lateral Bending using Linear Motor for Force Requirement Improvement.
Humanoid robots are similar to humans and can carry out human-like movements. Several humanoid heads, which include the neck, have been developed based on a variety of mechanisms with capability to meet requirements. In the field of robotics, challenges to the new mechanical solutions arise with mimicking the human movement. Existing robotic neck lacks some aspects like degrees of freedom and range of motion. Some humanoid robots exhibit only 3D OFs of the neck as featured from iCub and Floby, and only supports lesser weight than of the actual human head. With the complexity of robotic neck as part of the robotic head, the interest in its innovation became a mainstream. In line with this, the proponents studied the latest development of mimicking robotic neck and focused on achieving the desired response. An example of this is based on the study entitled Application and Implementation of Ball Joint for Mass Support of Neck Mimicking Movement by Kabag, year 2013. Their paper presented a humanoid neck featuring a ball joint mechanism integrated with revolute-like mechanism to support the head with the mass of 5 kg and a movement-sensitive controller that uses a potentiometer. Servo motors were used as actuators for the system. The robotic neck can exhibit a normal 4 degrees of freedom, but there is some deficiency. Insufficient value of torque for the servo motor, which has been used as the actuator, resulted to the inaccurate movement of the robotic neck, and this became the drawback of their study. Based on their study, torque of the servo motors greatly affect the movement due to the weight compensation. Since their study also focused on mimicking the movement of human neck aside from mass support, they mentioned that after evaluating the results of the prototype compared with the controller, lateral bending to the right and to the left has 53.10% and 46.36% percentage error respectively. The percent error of the Hyper-Flexion is 29.49%. With the aim to meet the force requirement to mimic lateral bending and Hyper-Flexion extension movement, the proponents introduced the idea of using new actuator that is related to the human neck anatomy, which best suits in the design and applicable in the robotic industry. Linear motor is preferred to be used since the design requires lifting heavy weight and actuator produces high force. To mimic the neck movements, critical designs are created and compared with the help of different studies. And using SolidWorks simulation, the proponents was able to design and test the prototype. The concept of Stewart platform will be used for the mechanism of lateral bending and lower extension flexion, while a servo placed at the top of the designed mechanism will act as the rotation movement of the robotic neck. The proponents came up with an idea of connecting the linear motor to a roller for the hyper-extension flexion. The evaluation results and different degrees of freedom of the current study are all outstanding. The current study performed better mimicking capability as compared with the previous study. The previous study indicated that torque of servo motor they use greatly affects the movement due to weight requirement and it caused a high percentage error. Our study created percent error less than 10%. It implies the linear motor is better to be used since it produces a force that is able to support the weight of the head while performing its mimicry.
Given the data, the mass of the robotic neck is 5 kilograms. To prove if the mechanism is possible, we use SolidWorks motion analysis. We then obtain the maximum exerted force of the linear motor, for each degree of freedom of the robotic neck. For hyper-flexion extension movement of the robotic neck, producing an angle from 30 to -10 degrees, the maximum required force is 49 Newton. For atlanto-occipital flexion extension movement of the robotic neck, producing an angle from 10 to -30 degrees, the maximum required force is 34 newtons. For lateral bending movement of the robotic neck, producing an angle from 45 to -45 degrees, the maximum required force is 44 newtons.